spaces. You welcome Dr. Tabiri to talk to us.
Thank you, David, for the introduction, and thank you, Jared, for the invitation to speak. My talk this afternoon will be on plane curves, which are quantum homogeneous spaces, and it is joint with my supervisors, Ulrich Kramer and Ken Brown. So the copies of these are on the archive if anyone would like to check them out. So an outline for my talk I'll start with a motivation for our research, some preliminaries. We'll look at what an algebra is, core algebra is, Hopf algebra. We'll do it quickly. People already know it. We'll skip through that fast. But for the audience who don't know it, we'll just do a brief recap of what a Hopf algebra is. Then we go to the main results for our work. So we came out with these new Hopf algebras, which we call AXAG and AFG, which come from some plane curves. Okay. So let's start with the motivation. So there is a classical correspondence between affine commutative Hopf algebras and affine algebraic groups over a field of characteristic 0. So given an affine commutative Hopf algebra, I've not said what a Hopf algebra is, but underlying a Hopf algebra is an algebra structure. And since it is commutative, any commutative algebra is isomorphic to the quotient of the polynomials in some number of variables by some ideal I. So given this algebra structure, you get an affine algebraic group by looking at the zero set of that ideal. Then in the other direction, given an affine algebraic group, if you look at the coordinate ring of the group, so you can think of them as functions on the group, that is a Hopf algebra. It is an algebra, but the Hopf algebra structure is given by the coproduct being defined by this. So for us, we are interested in some links between algebra and geometry. So we were thinking of, okay, so given an affine algebraic group G and a closed normal subgroup of this group H, then the space of cosets G mod H is an algebraic variety. So given that it's an algebraic variety, we can find the coordinate ring of that, and that would be a Hopf algebra. But also, your group acts on your space of cosets. It doesn't just act, it acts transitively on your coset space there. So we call any space which a group acts transitively on it a homogeneous space. So we were looking at non-commutative analogs of this. So instead of looking at commutative Hopf algebras, what if we consider non-commutative affine Hopf algebras? What would be the analog of you having a group acting transitively on your space? I think naturally you think of you looking at not just
Angela, is it possible you can please turn on your video, if possible?
Okay, so just a second.
Thank you.
Okay, I'll send it on another device. Okay, thank you. So, when you think of groups, Hopf algebra is generalized groups. So now if you are looking at non-commutative generalizations of this, you might think that if you want to look at non-commutative analogs of the homogeneous space, then you can think of quotients of a Hopf algebra by some Hopf subalgebra, but that definition tends to be restrictive. So it turns out that the right analog of this will be you not considering Hopf subalgebras, but things that we call right or left square-ideal subalgebras of your Hopf algebra. And the geometric property of transitive group action on this side of the correspondence corresponds to the algebraic property of faithful flatness. So these non-commutative analogs that we will find out will be quantum homogeneous spaces. So we will define them using faithful flatness property. Okay, so now we're done with the motivation, now some preliminaries. So if you know what a Hopf algebra is, I think just pardon us for the next few minutes. So what is an algebra? So given a set, an algebra is over a field is a vector space with two maps, your multiplication and your unit maps, such that some two diagrams commute. So the fact that this diagram commutes means that you have your associativity property, and the fact that this diagram commutes means that you have your unit property. So think of complex numbers. You can multiply complex numbers, you have a unit there. Or think of the group algebra. So group algebra, given any group, look at formal linear combinations of elements in your group. Then we can define some products on it, and that would be, it will be associative and unital. So we call that an algebra. But very often when we have an algebraic structure, we try to dualize it. So we dualize an algebra to get a co-algebra. How do we get this? We reverse the arrows here to get the dual structure, which we call a co-algebra. So a co-algebra is also a vector space over some field together with, so the dual of your multiplication now becomes this delta, and the dual of your units becomes this epsilon. So when you dualize the associativity, you get a co-associativity property here, and when you dualize your units, you get your co-units here. So we call this delta co-product or co-multiplication, and we call the epsilon the co-units. Okay, so an example will still be the complex numbers. So take the complex numbers. We know it is an algebra, but the co-algebra structure is defined on 1 to be just 1 since 1, and the co-units is just 1. And similarly, the group algebra is also a co-algebra. We define it to be, is enough to define it on the group. So we define the co-product on each group element to be just the tensor product of the element with itself, and the co-unit to be likewise. Okay. So now we know what an algebra is and what a co-algebra is. But now we want those two structures to work very nicely, and that leads us to what a bialgebra is. So we combine the algebra, co-algebra, but we want some compatibility conditions to hold. So given an algebra and a co-algebra, we say that it's a bialgebra. So bi means both structures are satisfied or compatible. If first your A is an algebra, but also a co-algebra, such that your multiplication, your co-multiplication work very nicely. So the compatibility conditions are either after you so co-multiplication just splits your elements into 2. If you split an element into 2 and multiply it, you want it to be the same as you first multiplying some elements before you split them up. Or equivalently, if you split them and multiply, you want it to be the same as you multiplying and applying the co-product. Okay, so that's what a bialgebra is, and the group algebra satisfies this property. So that will be one of our examples. I'll run through until we get to a half algebra. Okay, so we now know what an algebra is, a co-algebra is, and a bialgebra. So the final ingredient to a half algebra is what we call the antipode. So given a bialgebra, we say it is a half algebra if you have a homomorphism on your set A such that this diagram commutes. So this S here we call the antipode. It is an anti-homomorphism, so it reverses the order of your multiplication. So this diagram commutes means that if you start with an element in A and your co-product splits it into 2, your first element, you act on it with S, you do nothing on your second, and you multiply. You want it to be the same as after you split it with your co-product. Instead of, in the first case, you acted on S with the first component, but now you flip it. You do nothing on your first component and you act on S in the second component and you multiply. You want this to be the same as you first applying your co-unit and your units. So we call this the antipode property. So if you have a bialgebra with this antipode property, then we say it is a half algebra. Okay, so we saw that the group algebra was a bialgebra. So all we need to define it to be a half algebra is to define what the antipode is. So the antipode you can think of as a generalization of the inverse map in the group, because half algebra is generalized groups. So you define the antipode on your group elements to just be the inverse of your group elements. Or if you know what a universal enveloping algebra is, then it is also a half algebra. Okay, so we now know what a half algebra is. But these two examples are classical examples. Classical in the sense that if your group G is abelian, then your group algebra is commutative and your underlying half algebra is commutative. But also, if you look at the co-products, if you define some a map which we call the flip map, so if you define a map tau, which just takes an element, it just takes an element A tensor B to B tensor A. So we call this the flip map from A tensor A to A tensor A. So if you compose your flip map with your co-product and it's still the same as your co-product, then you say that your Hopf algebra is co-commutative. So when we say classical Hopf algebras, we mean Hopf algebras which are both either commutative or co-commutative. But we are interested in non-classical Hopf algebras. So that means they are neither commutative nor co-commutative. So an example of a Hopf algebra which is neither commutative nor co-commutative is, when you had a free algebra on the generators x, y, a, b, and you mod that by the ideal of relations. So you want your x and y to commute, your a and b to commute, your a and y to commute, your b and x to commute. But you also want some extra conditions here. So we will see why this was one of the motivating examples. So here you have an equation of a curve which we will see is sketched in the next page. But you have some other relations here. This relation, we are saying that our b and our y anti-commute and our a and x commute up to a primitive third root of unity. So it is an algebra, but a co-algebra with x and y skew primitive and your a and b group-like. Okay. So we know what a Hopf algebra is, but now we need two more definitions to define a quantum homogeneous space. So if I have a Hopf algebra and you have a sub-algebra of it, such that the image of that sub-algebra is contained in that sub-algebra tensor H, then we say that that sub-algebra is a right co-ideal sub-algebra. Or equivalently, is a left co-ideal sub-algebra if its image is contained in H tensor B. Okay. So now we define our final ingredients, define what a quantum homogeneous space is. So if you recall from the motivation, we said that the geometric property of transitive group acting on a space is reflected in a faithful flatness property. So what is faithful flatness? So given a module over a ring R, we say that that module is faithfully flat as a left and right R module, if and only if your functor M tensor R is faithful and exact. What is this? It means that if you have any sequence, that sequence is exact if and only if after applying your tensor, your functor, it is also exact. So this property of faithful flatness is something that is sometimes challenging to prove directly, but an example of a faithful flat module is free modules. So free modules, think of modules which have a basis. So all modules do not have base, but the special ones that have bases are called free modules. And in our work, we prove this faithful flatness property by finding a basis. So showing that our modules that we have are free modules. So we now know what a Hopf algebra is, and right co-ideal sub-algebra is, and faithful flatness. So finally, we can define what a quantum homogeneous space is. So given D, a sub-algebra of a Hopf algebra, it is called a quantum homogeneous space if it is a right co-ideal sub-algebra of the Hopf algebra, such that H is faithfully flat as a left and right P module. Okay. So when I started my PhD, we were interested in non-commutative generalizations of the classical correspondence that we gave. So instead of looking at affine algebraic groups, we were considering singular plane curves. So the singularity will mean that it wouldn't be in that classical case. And we were looking at non-commutative analogs of a homogeneous space. So when I started my PhD, we had worked on this example of the cast. So the cast is sketched this way. So it has a singularity at the origin. So he showed that this was a quantum homogeneous space. How? By defining some Hopf algebra such that the coordinate ring of your cast is your Hopf algebra is faithfully flat as a module over the coordinate ring of the cusp. So when I started, and the Hopf algebra structure he used to show this is the Hopf algebra example we gave here. So in this example here, if you look closely, you realize that the first line of relations here are just commuting variables. This here is because we want our coordinate ring to be a subalgebra of it, but there are some other properties, relations here. This relation, we are saying that A and X commute up to a third root of unity. So I tried to use this example to prove that for another example to see if this would work in that setting. And that first example was the nodal cubic. So the nodal cubic looks like the cusp, just that you've added a degree 210 here. So we tried to see, well, that's the algebra, Hopf algebra we defined, he defined for the cusp, will it work here? It turned out that it wouldn't work. Why? If you define the relation between A and X to be they commuting up to a third root of unity, when you apply that here, you wouldn't get it to vanish when you apply it to this relation of your nodal cubic. So we had to modify it a bit. How? So we still maintain these relations as he had, but we had to modify and that of the anti-commute of that B and Y. But we had to modify the relation between A and X. Why? Because in the end, you want your coordinate ring of your curve to be a subalgebra. What is a coordinate ring? So in the coordinate ring of your curve, our Hopf algebras are generally non-commutative. But in the coordinate ring, your X and your Y commute. But also you want your relation for your curve to go. So that means that your co-algebra structure should respect that relation. So when you apply that, you realize that you need some terms to go to 0, and that will give you these two relations here. So we looked at this, and it looked very strange that it worked, because here you have some permutations of 2a's and 1x. You have a monomial of with degree 2. Then similarly, you have some permutations of now 1a and 2x's, but now you have permutation of 1a and 1x. But if you also look closely, you realize that if you define, let's say, the degree of a monomial to be, let's say, the sum of the individual degrees, then you realize that all these three terms here have degree 3, this one has degree 2, all these three terms here have degree 3, these have degree 2. So it is mimicking your original polynomial you had here, degree 3, degree 2. But also, your A variables here are all the same. So you have 2a's here, 2a's here, 2a's here, 2a's here, and similarly 1a, 1a, 1a. So we started with this example and it worked, and for us, okay, it was great to, when you're starting your PhD, to have something work, but we wanted to see why did it work? Was it just by chance, or there was something more into it? So he asked me to try this other example of the lemniscate. So the lemniscate is given by the equation y squared equal to x squared minus x to the power 4. And you can, it's sketched as this, so it's just the infinity symbol. So I started with this, and it seemed to work. How we defined, of course, the algebra structure wasn't given by these same relations, but it was similar. You could see a pattern of some permutations of some a's and x's, they having the same number of a's. So it worked, and we tried it for some other examples. But one thing that seems like a pattern here is that if you look at the cusp, on your left-hand side, you have just a function of y. Nodal cubic, just a function of y. The lemniscate, just a function of y. But also, when you look at the right-hand side, you just have a function of x, a function of x. So we do not have any mixed term here. So there's no xy, x squared y, or anything of that sort. So we realize that our theory works in general for any plane curve which can be written as a function of y equal to a function of x. So that led us to this definition. So this definition is not ours, we found this. So that those curves, we call them decomposable. So a plane curve is called decomposable if you can write it as a function of y equal to a function of x. Okay, so one will ask generally, can every plane curve be made decomposable? The answer is no, but you can do it sometimes. And there are papers telling you when you can and when you cannot. But some cases it works. So for instance, if you consider the coordinates crossing xy equal to 0, then you can transform it by just rotating it and you get a decomposable curve equation y squared equal to x squared. Okay, so this theory worked and we decided to develop it more to prove that some class of plane curves are quantum homogeneous spaces. Okay, so our main theorem for today is that decomposable plane curves of degree at most 5 are quantum homogeneous spaces. And for us, we wanted to prove this in general. We conjectured that it holds in general, but currently our proof, as I mentioned, we use the faithful flatness by finding a basis. And for basis, we use Bergman's diamond lemma. And for the lemma, we have to resolve ambiguities, and the process becomes very long, writing computationally if the degree is greater than 5. But we see a pattern which we think holds in general, but for now, we only have a proof for up to degree 5. Okay, so how do we prove this main theorem? So we construct these new Hopf algebras motivated by the previous example. So how do we do it? So we have a decomposable plane curve, f of y equal to g of x. Now we want a Hopf algebra which has this as a right-sided subalgebra. What does it mean? It means that we want the image of our generators to be a subset of, to be contained in B tensor H. So B here, I mean the coordinate ring of this curve. Similarly, the image of your generator Y to be contained in this. Now, if you want this to hold, then, and also for this to be a Hopf algebra, or even a co-algebra, you need these to be co-associative. The delta must be co-associative. So when you check the co-associativity property, so we start with some random variables A0, A1, A2, B0, B1, B2. But co-associativity forces A0 to become X, it forces A1 to become X, and it forces A2 to be some group-like element, and similarly for your Y. So we start with that and we get a right-wide subalgebra. But for the faithful flatness, we will use Bergman's diamond lemma to prove this. So this whole approach of you finding a way of defining Hopf algebra in a way such that you want some relations or things to hold is attributed to Manin. So he has a paper where he discusses this. So if you'd like to check it, you can. Okay. So now let's see how this Hopf algebra AXAG is constructed. So now we define this algebra, the free product of your polynomial in X with the Laurent polynomial in A. And we define a filtration on the subalgebra of this generated by X and A. Because if you look up in the relations we had above, the bad relations were between A and X. So now we decided to split our proof into two parts. Deal with A and X, deal with Y and B, bring them together, and you get a bigger Hopf algebra. So now we are concentrating just on A and X. So you define a filtration of the subalgebra generated by X and A. How you give A degree 1, 0, we give X degree 0 and 1. And you define some PJIs to be the sum of all monomials of degree JI in this subalgebra, where your J is running from 1 to n minus 1 and your I is running from 0 to n minus 1. So I forgot to add, so my n here is the degree of your polynomial G. I'll come back to it. Yes, so here. So G is a polynomial in X of degree n, and we want it to be the degree to be at least 2. So maybe let me go back and give you a feel of what these PJIs are. Okay, so now let's go here. This was our motivating example. So we said degree of A is 1, 0, and degree of X is 0, 1. So A squared X will have degree 2, 1. This will have degree 2, 1, 2, 1. Similarly, this will have degree 2, 0. And these here will have degree 1, 2, 1, 2, 1, 2, 1, 1. So in terms of our PIJs, these three terms here are P2, 2, 1, because we said it was the sum of all monomials of degree 2, 1. And similarly, these 3 terms here, this, and this are the sum of monomials of degree 1 and 2, so it is P1, 2. And similarly, these 2 terms here, the AX and XA will be P1, 1. So this here will be P1, 1. And similarly, this term here, A squared here, will be P2, 0. So this here will be P2, 0. Okay. Now, as I mentioned initially, we see that the A degrees are the same for each of the P's in our relations. The A degrees are the same. Okay. So now we define this algebra we are interested in. We call it AXAG. So your G is coming from the right-hand side of your decomposable blanket. We define it to be the quotient of your free algebra by some relations. What are these relations? So in the relations, we are trying to, G is a sum of monomials. We are now going to replace those monomials here by these PJIs. But we are running from J equal to 1 to n minus 1. So we are going to replace our monomials in G with it. And let's see an example here. So the example will be that of the nodal cubic again. So our nodal cubic was given as this. So our G here is x squared plus x cubed. And our relation said that we are running through by looking at all permutations of some number of A's and X's. So here this will be, we said this is P21, this is P20, and that, and similarly that. So because our degree here is 3, we said our relations will have n minus 1 relations. So we have just 2 relations. Yeah. So these are the relations giving your algebra AXAG. So it is an algebra, but also a Hopf algebra. How? By defining your co-product of your X to be 1A's cube primitive and your A to be group-like. Okay, so we have this, but what do we need? What do we do with this? Let's first look at some examples which relate to some already known algebra. So when degree of G is 2, then you're defining relations. So since your degree is 2, how many relations do we have? We said the relations are n minus 1, so we have only one relation. And that relation is given by this, where this is your G. We can transform this into A and some, let's say, X prime at anti-commuting. And this is already well known as the quantum plane at Q equal to -1. But when degree of G is 3, then we can identify this Hopf algebra AXG with some already well-known algebras, which are called down-up algebras. How we can define some filtration, and the associated graded algebra will be isomorphic to. So if you already know what a down-up algebra is, they are given by some parameters. In this case, our Hopf algebra will be isomorphic to the down-up algebra A minus 1, minus 1, 0. And for us, this helped us in finding properties for our Hopf algebra when our degree is 3. Okay, so what are these? These are Hopf algebras, but what are some of their properties? So they are pointed. What does it mean? They are pointed because every simple sub-algebra is one-dimensional, and this you get from the fact that our Hopf algebra is generated by an invertible group like and a skew primitive element. This is we haven't shown this entirely, so I'll take this out. I won't talk about that. But we also found out that it has a basis. It has a basis up to degree 5. And that was what I mentioned in the main theorem. It has a basis up to degree 5. How? Your basis is in the form, you put all your x's to your left-hand side. You have some u there. I'll tell you what these powers of u are. And you put all your a's to your right-hand side. And what are these u's? So these u's belong to a set. So you look at permutations of a and x's, whose degree is is less than your degree of your polynomial n. So for instance, if your n is 3, then this set LA here will just consist of AX. So your basis will just be powers of X, powers of AX, and powers of your A, which are also the same basis of a Downer algebra. But when your degree of your n goes beyond 3, then this set here will have more than one element. So if your n is 4, then there are different possibilities for your R and S. So you have AX here. That's when R and S are both 1. You also have A squared X here, and you also have AX squared. So this here will form a free algebra, which will make things explode for us, because for us we wanted some algebras which grow polynomially, but it seems things go really bad when the degree exceeds 3. So nice properties happen when degree is 2 or 3. So they are Noetherian, domain-observable, ideally finitely generated, and they have finite GK dimensions. So GK dimension, think of the polynomial ring in n variables. It grows. Its GK dimension is n. So we look at how our algebras grow, and it turns out that our algebras, apart from degree 2 and 3, they have infinite GK dimensions. They become they grow too fast. Okay, so now we have our Hopf algebra AXAG, but also we can define a similar Hopf algebra for the left-hand side of our decomposable plane curve. So now instead of having X in your construction, replace it with Y. Instead of having A, replace it with B, and instead of having G, replace it with F. So you get these two Hopf algebras. Now we get our bigger Hopf algebra by tensoring these two Hopf algebras and modeling out by only two relations. The two relations, one is coming from the plane curve and the other is coming from this. So our M here is the degree of our F, and our N here is the degree of our G. So this is not just an algebra, it's also a Hopf algebra with the same Hopf algebra structure we had on the other algebra. Yes, and we're able to do this. So these two relations here are coming from the fact that you want your co-products to respect these. So your co-product of this, because you define your co-product of your A to B. So we defined the co-product. So we define the co-product of A to be 1. Not A, I meant X. So we define our co-product of our X to be 1 tensor X plus X tensor A, and that of our Y to be similar. So if you compute your co-product on these, it forces this other relation because your G has degree n. So when you compute the co-product of your G, it will turn out to be this. It will also become skew primitive. It turns out to be just this, and G times A to the power n. Okay, and similarly, when you do the co-product of your F, it becomes similar to that. So that forces us to apply this relation A to the power n equal to B to the power n. So we have a Hopf algebra, but not just a Hopf algebra, but we also get that it is also a free module over the coordinate ring of your decomposable plane curve. So we started with the example of the nodal cubic, which we showed works nicely, but we also looked at the lemniscate. So the lemniscate, I sketched it initially. So in the lemniscate, you have three relations. So the relations coming from permutations of 3 A's and some number of X's, 2 A's, 2 X's, 1 A, and 3 X's. So we showed that these are examples, and in general, decomposable plane curves are quantum homogeneous spaces. So in these, the coordinate ring of any decomposable plane curve will be a right-for ideal subalgebra of this Hopf algebra A and G. But for the faithful flatness property, we use Bregman's diamond lemma. So how? So we want to find a basis of this over your coordinate ring. So we try to pull the x and y variables to the left-hand side, because we can do similar with the right-hand side. And in the middle, you have some terms here. So this u here, I define it above. So there are some permutations of a and x's. These v's here are permutations of y and b, and your powers of your a and b. So for us, we used the Bregman's diamond lemma to prove the faithful flatness. So it gave us that if you have a decomposable plane curve of degree at most 5, then this coordinate ring is a homogeneous space. But before I finish, what are some of the properties of this Hoff algebra here? So it turns out that it also has nice properties. If in general this Hoff algebra is pointed, but if you want nice properties of it being Noetherian and finite GK dimension, then as similar to what we had for the AXAG, you have nice properties when the degree of your polynomial is at most 3. So if you have degree at most 3, then it is Noetherian. If it is has degree at most 3, then the GK dimension you do you add these degrees and do some subtraction, then it give you a finite GK dimension algebra. So these are some of algebras that we discovered. Some of them are related with Dharma algebras, quantum plane, and all that. But the Hoff algebras we found, they are Hoff algebras in general. So for any degree n polynomial, it is a Hoff algebra. But for us, we only showed the faithful flatness property for up to degree 5. But in general, they are Hoff algebras that have been discovered. And there are some open questions from it. So yes, and there are more coming up. So now, instead of constructing this for decomposable plane curves, can we do this in general for any curve which even has mixed terms? So you could have x, y, x squared, y. Can you do something similar for them? And what about the faithful flatness property? So when I look at my thesis, so in the appendix, I did a lot of computations for this resolving ambiguities for us to use Bregman's diamond lemma. It was quite a lot, right? But can we find another concise or maybe elegant way of proving the faithful flatness property, probably without using Bregman's diamond lemma, or probably seeing a pattern in it that would give us a very concise proof? And also, these Hoff algebras that we discovered, are there any isomorphisms between them, and what are the conditions you need to have an isomorphism between them? Do you need them to be isomorphic only when their degrees are the same, or do you even strictly want their coefficients to be the same? We still don't know, and there is some more. So some were asking what are their representations. We haven't computed the representations of these algebras. Some were asking of the Hochschild cohomology. So these are all open questions we are trying to see, because probably when we go through these, they will give us a better understanding of these Hoff algebras. So yeah, I think I've spoken very fast, and that's the end of my talk. And thanks for the invitation.
Yes, thank you so much, Dr. Tabiri, for the talk. Indeed, we have learned something, at least for me. I know now very well what a Hoff algebra is, a decomposable curve, and I can confidently say to a decomposable curve, you can associate the Hoff algebra with some interesting properties. Thank you for keeping time. We still have about 19 minutes. So if members have questions, comments, this is the time. Any questions, comments?
Maybe I'll ask a question.
Please go ahead.
So you talked about curves all the time. Can you do something for surfaces? I don't know. Is there some interesting story here for higher dimensional spaces, or is it very restricted to curves?
So we haven't explored it, but I think it will work for, let's say, in three-dimensional space, when you can only decompose it into just there's a function of x, y, and z, you wouldn't have some mixed term there. If you don't have any mixed term there, I think it will work, but we haven't worked. If you have mixed term there, our theory doesn't work when you have mixed term. But if you have, for instance, for the sphere, of course, the sphere is already homogeneous, so I think for the sphere it would work. But we haven't explored this in general.
Thank you.
Any more questions? You're welcome to write in the chat if you are not happy to speak. So as we perhaps we wait for more questions, let me utilize this opportunity to announce 2 events that are going to take place next week. The first one will be on Thursday, the 18th of November, and that is a workshop on the Ganbo project. The workshop will be about algebraic biology. So an email was sent out to the usual participants, but those who might have missed that email, they are welcome to check the FMIS website. The second event is the conference, which will last for 2 days. It starts on the 19th, and that will be a Friday, and it will go on even on Saturday, the 20th. This conference will be about how to do online teaching, how to do this in mathematics. So encourage your friends and colleagues to register for this conference. And to our new participants, in case you joined today, these seminars are weekly. So every Wednesday, starting at 3 p.m. East African time, there is always a seminar. And you can register still so that an email can be sent to you with a link to accessing the seminar. I'm not seeing any more questions here in the chat. George Barra, some question, could the same construction apply to curved surfaces in the projective spaces? Yes, Georgia has a question.
I think it's similar to what the question that was asked before. So for now, we work just in the plane, but we think it will work for higher dimensions if you don't have mixed terms in the way your curve is defined. But we haven't proved this, so it's still open. But we think it will work, but we haven't shown it. George, I hope that answers your question.
Yes, if there are no more questions and comments, please unmute and thank Angela by clapping.
Thank you.
Yes, thank you so much. Yeah.
Video.
See you next week at the same time.
Thanks for the invitation.
Hello.